Hi, Dirk. Good morning. So Dirk will be here. You are muted. So you will be here, yes?
I will be here for the beginning of the speech to
Okay.
give my support to Geert, my colleague.
Yeah. I have a very big apologize because our rector is gathering us.
Mhm.
So could you just introduce him, if
I can.
possible,
I
please?
can.
Thank you. Thank you.
Geert.
So can you hear me now?
Yes, I can.
And you can see my screen.
Yes.
Perfect.
Okay. So
Yes.
let me. So I've just been asked to introduce my colleague Geert van Ulle. So we're both in the Spacecom project from the AP University of Applied Science and Arts in Antwerp in Belgium. Maybe some of you already witnessed or visited or enjoyed my presentation at the beginning of this workshop series, my presentation about FPGAs for space applications. And now my colleague Geert van Ulle will talk about the software-defined radio for space applications. Now, Geert and me, we both work for in the course of software-defined radio, because FPGAs and software-defined radio, they are a good match, because most of the software-defined radios are based on FPGA technology. But I'm not going to spoil this for Geert. I will give him the floor, and I would say to the rest of you, enjoy this this session. So Geert, if you're ready, the floor is yours.
Yes. Oops. I see the image is disappearing. Yeah, this looks better.
Yeah.
There we go. Very good morning. Welcome to my session on software-defined radio. Of course, I'm not aware of what you know already about SDR. I guess the levels will be different depending on who. So I've tried to compose something where I go from introduction level all the way up to like a stage where you could almost immediately use it. So first of all, why would we use SDR in satellite communication? Well, let me start with this remark of John Getmark. The satellite world has been unfortunately stuck in the analog radio age up until very recently. And this is very true. So as he says, the radio waves going up to the satellite, the satellite will take in the radio waves, essentially just repipe them down without ever digitizing the signal. The signal stays analog the whole way through. And this is the situation that we have in satellite world, mainly in geostationary satellites, but also on other types of satellites. And if I take this practical case here, the fact that signals stay analog in satellite doesn't mean that we are not transmitting, of course, digital signals over satellite. So if I use this example of an SAP single channel per carrier signal going up to the satellite, a digital signal using DFBS2 and QPSK as modulation, it goes to the satellite, goes into a linear transponder, and the signal comes back just exactly the way we send it up, and it goes to the receiver sites or the receiver sites when it's a contribution signal. So suppose this customer using the satellite link has leased out his transponder, but now is planning to do some changes and having 2 different locations to create his signal. So he could use the same bandwidth because we have some new technologies, of course. We have DBS3 that allows more data to be put into the same bandwidth. We can go from QPSK up to 8 PSK, again, increasing the possible data that the amount of data that we can squeeze into the same bandwidth. So the customer can use his same transponder, putting up 2 slots next to each other, but then there's a problem. The satellite doesn't do any processing. So how does this work normally nowadays? Both of these new signals will be downlinked again in a ground station. The DVB-S3 8PSK will be demodulated, either decoded or just remodulated right away, depending if the transport streams are usable. And it will be modulated again in DFBS2 QPSK, sent back up to the satellite, and then it goes back to the receiving stations for a contribution receiving. So what we see here that all of a sudden we don't need 1 transponder slot on the satellite, but we need 2. So the bandwidth doubles. The customer all of a sudden sits with a double, has a double of costs of leasing space on satellite, but also has a permanent cost on renting out equipment in the ground station to do this turnaround. So this is actually also a business model, of course, for the ground stations. They live from these kind of turnaround. But of course, from the standpoint of the customer, this is not ideal. What would be better, of course, if the satellite could do this processing and send the signal back down to Earth, but there is no processing capability on board the satellite. A second example is the now increasingly popular CubeSats. Now, CubeSats, I saw that in the program there's a talk on CubeSats already, so I don't really have to explain what a CubeSat is. But these CubeSats, in general, they come in constellations. So CubeSats are just small satellites, form factor 10 by 10 by 10 centimeters, or a multiple of that. And they form constellations. We will use them, for example, if you compare to mobile network, you have a constellation of CubeSats that will actually do a roaming, where you have a mobile phone in a car switching over from one antenna to the next one on the ground. Here we have the opposite. Now the connection point stays physical on the same spot, maybe, and the handover is like a roaming from the one satellite to the next. So this is more or less how these constellations work. But of course, imagine we have this kind of constellation, and there's a competitor coming into the market. Now, these constellations typically consists of a few thousand satellites, let's say 3,000 up to 5,000 satellites in low orbit, forming these constellations, and they have links in between them. So they do, of course, the data transfer between the satellites. So if you do a handover from one, that all these tiny satellites don't have a turnaround back to multiple ground stations. That would be unworkable. So they communicate directly between them. Now, if we have a competitor entering in the market, putting up a new fleet of 5,000 satellites, well, what's to say that it doesn't create any disturbances in the existing constellation that's already there? So it could be, for example, that the links between the CubeSats are disturbed. There's some spurious signals that enter into the receiving side between the satellites from this new constellation. Actually, this could be resolved very easily. It could be as easy as putting a notch filter at the entrance of the receiver to reduce this disturbing signal from the received signal, and the problem solved. Of course, how do you add a notch filter in 5,000 orbiting satellites? Now you can't just go grab them out of space and modify them. So this also is a clear example that a way to address these hardware problems in a different way is actually needed in space. Now let's look at software-defined radio. What would it be great if we could replace this dedicated hardware in some form or another with a general computing device? If all these processing functions that we normally do in hardware, if that could be done in software. And that's what software-defined radio does. The principles are we will digitize the RF signal as close to the antenna as possible. We will do so using IQ sampling techniques. So we arrive in the complex number field. We will perform the signal processing on a mathematical level, and then we will convert the signal as late as possible into the stage close to the antenna as possible, so that all that we need is an RF stage on the output. So these are the main SDR principles. So if you compare that with a conventional receiver, just to give an example, what the benefits could be and how this processing can save a lot of hardware and components is, for example, just in a receiver, a double heterodyne receiver has some converting stage from a first IF frequency to a second IF frequency, for example, typical 10.7 megahertz down to 455 kilohertz. This is a typical narrowband receiver. So what we see there, that we will have an amplifier, we have a mixing stage, an oscillator feeding the mixing stage, and then we have a bandpass filter at the output. This is a way that we would go from this 10.7 megahertz down to the 455 kilohertz. Now, this gives us a complete hardware circuit with transistors, a lot of components. It's all analog, so we have to compensate for a lot of stuff, for temperature, for drifting. Components have, of course, tolerance, and a lot of things can go wrong there. So it's quite an effort to build these kind of converter stages. If anybody has done this already practically, you know that to get, for example, a propagation delay constant, all these kind of things, it's not so easy to design a circuit like this. Now look at the transposed circuit in software-defined radio. What we would do is we digitize the signal, we go from the analog to the digital, and then we process it in software. And what would this mean? The stage going from 10.7 megahertz to 355. Well, we have an incoming signal that is 10.7 that contains some useful information on the carrier wave, and we need to reduce the frequency. So what we will do is we will just drop a few samples. Now, so we call this decimation. Out of the number of samples that we have at the input stage, we just drop a number of samples, and we have a lower frequency at the output that still contains the same information. So this is a very easy mathematical operation inside a general computing device that obtains exactly the same thing. Now, if we look at modulation, for example, if we want to make a transmitter, well, that's a little bit different. We have a carrier wave, for example, here. We look at the mathematical expression of that. That would be the amplitude multiplied by the sine wave of the rotating angle plus a phase, for example. that is fixed. And the modulation, as an easy example for a modulating signal, we also take a sine wave. So we have the same formula, an amplitude multiplied by the sine with a rotating angle. Now, what would be an amplitude modulation signal in this case? Well, it's this formula. Now we will have the amplitude of the carrier wave being modulated with the sine of the modulation. So this is quite a complex formula, and sine waves to be calculated by a CPU is not so easy. In general, they will use tables for that, because like if a sine wave actually has to be calculated, that's even a lot more calculations. They will use tables with pre-calculated angles. Of course, this has a compromise on the accuracy of it. But even that will take some CPU load. So we have a lot of CPU load if we would like to do that. And that's not a really reduction. We would use a quite performant CPU to get these things done. So a performant CPU means also a lot of heat, a lot of energy. So this is not really a very good solution. And I take a small break here. If there are in my talk some questions, of course, feel free to interrupt me and ask them along the way. Of course, there's a Q&A at the end, but sometimes it's more interesting to have the questions on the moment itself. So this is not a really good solution to these calculations this way with a CPU, but we can look at signals in a different way. Of course, if you look at a sine wave in the time domain, that actually is also the same thing as a rotating vector. You know? And if we look at a phase diagram, we have a vector that is rotating with the frequency of the sine wave. Now, if we would compare this amplitude modulation signal in a vector diagram, as a rotating phasor, we would see this. We have actually a carrier that is a vector that is rotating with the frequency of the carrier frequency. And if you would add modulation to that, we could see this as an additional vector that is on top of this carrier wave. So we have the modulation, of course, with another frequency, slower than the carrier vector rotating around, but in a result forming a new vector, and this vector will actually increase in length and decrease in length according to the modulation vector rotating, which is just the same as the time domain signal of an amplitude modulation, where we see the sine wave going higher and lower in amplitude. So this is the vector expression of the amplitude modulation signal. Now, the advantage of this is that we can use a complex number expression in mathematics to describe these vectors. For example, the carrier wave here, we can express with the real and the imaginary part on the x and y axis. So the carrier wave becomes I plus j q. And that's the expression of the carrier wave. And we have the modulation, also the real and the imaginary part becomes I plus j q modulation. Now, what is then the amplitude modulation signal in this case? It's the complex addition. And that's very simple. We add the real parts, we add the imaginary parts, and we have a new vector with a real and an imaginary part, which becomes AM plus JQAM. So from the complex mathematical operations in a CPU of dealing with sine waves, we reduce the complexity to simple additions. Now that's marvelous. Of course, this is very easy to do, additions calculating with a CPU, and it's a beautiful system. Of course, this is an AM signal. Now, how do we go from here to all kinds of signals? Well, as an AM signal could be expressed as a complex addition. As a matter of fact, any type of signal can be expressed as a complex addition. Why? Well, we take Fourier. What is Fourier is saying that any signal, any complex waveform can be expressed as a series of sinusoidal waves. So we have an addition of a whole series of sine waves with different amplitudes and different frequencies that together make up another complex waveform. Addition of sine waves means in this vector field an addition of vectors. So we can express actually any random signal form as a summation of complex vectors. So this is beautiful. Any kind of signal operation becomes a complex operation of simple adding or subtracting complex signals. Now this leaves us with two major questions. First of all, how do we obtain samples in a complex number format? And the second thing is, well, we're talking about radio frequencies here. We're talking about hundreds of megahertz or gigahertz. So how are we going to sample these high frequencies? To answer these questions, we will use aliasing to our advantage. And for people who are not familiar with aliasing, I will quickly go through it. If we do a regular sampling of a signal, we go from a continuous wave to a discrete series of numbers. No? Shannon-Nyquist's formula says that we have to sample with the double of the frequency that we want to sample. Okay, so this is the typical sampling formula. Now, what is then aliasing? If we sample a certain frequency f2 with a sample frequency f1, we have the blue sine wave here. Well, there's also some frequency f2 alpha of a very high frequency or a frequency higher than the sampling rate that by coincidence fits all exact sampling points. So as a result, if we get the discrete sample values, we cannot distinguish whether the signal that we sampled, if it's f2 or if it's f2 alpha. So this high frequency could just as well be what we have sampled. And that is what we call an alias. f2 alpha is an alias frequency. Now, in general, how is this being solved? Well, we will add an anti-aliasing filter. We will put a low-pass filter after the sampler to filter out this f2 alpha frequency. Now, this typically results, this f2 alpha is preserved after sampling as a frequency on the position of f2. Now, if we would have another frequency that is above the sampling frequency, for example, f3 alpha, we would perceive it as the same thing as a frequency f3. So if we have the low frequency f3 or the f3 alpha frequency, after sampling, it would appear as it would be the same frequency. So what we see is as these frequencies that are higher than the sampling rate shift towards our sample frequency, they appear as a frequency closer to 0. So we have some kind of a linear mirroring of the frequencies above the sampling rate downward towards 0. Now, there's a second possibility of aliasing frequencies. We can have a frequency that is actually higher than that is actually lower than the sampling frequency, but is also projected into a lower frequency due to this aliasing effect. And any frequency above the half of the sampling frequency has this effect. And this is actually the reason why Shannon-Nyquist exists. No? It is because if we sample a frequency that is higher as the half of the sampling frequency, it appears as being a frequency lower than the half of the sampling frequency. So this is actually the reason for the Shannon-Nyquist formula. So the anti-aliasing filter normally would suppress all frequencies above half of the sampling frequency. And then we would limit all possible aliasing signals from being sampled. Now, if we look at a sample frequency here, if we have an alias, and now we have the other way around, if we now have an alias that is higher in frequency than the F2 alpha, for example, F3 alpha, that is closer to the sampling frequency, but it's higher than the F2, it appears mirrored below the F2. So between the half of the sample frequency and the sample frequency, what we have is a signal rise in frequency. They are mirrored as a frequency that is closer to 0. So we get a flipping of the frequency spectrum in this range. So this is something to remember. Now, if we look at aliasing in general, for any given sample range, so the red here are 6 samples, there are an infinite number of sinusoidal waves that we can draw exactly through these sample points that would exactly produce these samples, and thus the discrete sample results cannot tell anything about which one of these frequencies it is. So we can draw an infinite number of sine waves through these sample points. Of course, not random frequencies. They have to be a certain specific frequency, but we have an infinite range. So we have a multiple alias possibility. We have an alias that is below our sample frequency possible, and we have aliases that are above our sample frequency, up to infinity. Now, this is where we can use aliasing to our advantage. Because instead of having an anti-aliasing filter that is below half of the sample frequency, we could actually filter out just one of these frequencies that is higher than the sample frequency. If we sample it, we would get a discrete sample range, so we get discrete samples, but these samples would represent this frequency and only this frequency that is above the sample frequency. So with a lower sampling frequency, we could sample actually up to a multiple higher than our ADC actually is capable of processing. So this is interesting, and this is what we call oversampling. So due to oversampling, we could actually, with, for example, an AD converter that has a bandwidth of 30 megahertz, we could actually sample, for example, a 300 megahertz signal. So this is great. But what do we have to keep in mind? We can sample only one, what we call a Nyquist zone. So a Nyquist zone is, of course, the range of frequencies where we would not encounter the second series of aliasing frequencies. And this is better demonstrated here with the drawing. The Nyquist zones are every time half of the sample frequency. So we have a first Nyquist zone that is between 0 and the half of the sampling rate. So that's a nice zone. There won't be any aliases in there if we filter all the rest. A second zone would be between the half of the sample rate and the sample rate, or sample rate and 3/2 sample rate, and so on. So these are these Nyquist zones, and we could select with a filter one of these Nyquist zones, and that would be our oversampling range. The problem here that we have to keep in mind is that, well, as we had these low to high frequencies that were flipped in the Nyquist zone between half the frequency, half of the sample frequency and the sample frequency, we have this flipping repeating. So the third Nyquist zone will be linear mirrored, and the fourth Nyquist zone will be mirrored in the opposite sense again, and so on for every Nyquist zone. And a nice image to visualize this, what is really going on, it is as if the whole frequency spectrum is like these folding papers that you used to have in old printers, that you simply fold down the whole frequency spectrum onto one page. So the first page is normal, the second page is flipped, and then the next page is normal again, the second page, the fourth page is flipped, and so on. And this for the whole frequency spectrum up to infinity. So this is a nice visualization of what is actually going on with these Nyquist zones and in an oversampling situation. So now we have something said about the sampling of high frequencies, but we still need to address how to obtain complex samples. For that, we start with ordinary mixing. In ordinary signal mixing, what we have is we have an incoming signal going into a mixing stage, and this mixing stage receives a signal from a local oscillator. So what is typically happening in a mixing stage, that it will produce mixing products, being, for example, the input frequency minus the local oscillator frequency and the input frequency plus the local oscillator frequency. So what we would typically do is put a low-pass filter at the output of the mixing stage, so we have only the differential signal left. Right? So we have the input frequency minus the local oscillator, and that will be, for example, our intermediate frequency, our IF frequency. Okay. Now, if we look at the mathematics behind this, if we consider the local oscillator to be a sine wave and the input frequency also to be a sine wave, we have actually a mathematical multiplication of two sine waves. So we have the sine of the rotating angle of the input frequency multiplied by the sine of the rotating angle of the local oscillator frequency. And mathematically, multiplication of two sine waves can be written as following. So it's half of the amplitude multiplied by the difference between the rotating angles, the cosine of the difference between the rotating angles, minus the cosine of the addition of the two rotating angles. Now, here again, we can see what is happening when we add our low-pass filter. Our low-pass filter will actually filter out this cosine product of the addition of the rotating angles. So we are left with the cosine signal of the difference between the rotating angles, which is in fact the input signal minus the local oscillator frequency in a cosine form. Now, if I would mix instead of a sine wave my input signal with a cosine wave, I would get the multiplication of a mathematical multiplication of a sine wave of the rotating angle of the input frequency with the cosine wave of the rotating of the cosine function of the rotating angle of the local oscillator, what gives me 1/2 of the amplitude of the addition of the rotating angles sine plus the sine function of the difference between the rotating angles of the two signals. Now here again, adding the low-pass filter mathematically is the same as deleting the summation function here of the two rotating angles. So this part of the formula will disappear, and we are left with the input frequency minus the output frequency, but now we get the sine wave. So here we see that we can produce from an input signal, of course, we have a mixing stage, so we will have a down conversion of the signal, but at the same time, we will have the cosine and the sine result of that input frequency, of course, at a lower frequency. But we are not interested in the real frequency. We are, of course, interested in the content that is in this carrier wave. And for that, we have sufficient with these cosine and sine values, which is actually a complex sample, because the cosine axis is the real part of a complex signal, and the sine axis is the imaginary part of a complex sample. So we get these two results, cosine value, the cosine value plus j, the sine value, which gives our complex sample. Now, how do we obtain this in a hardware version? Well, this is the circuit. We start with a local oscillator that is getting the RF signal into a mixer. The output of this mixer, as we have seen, is the cosine wave. And this local oscillator, we will shift the local oscillator with 90 degrees, what will produce us a cosine wave of exactly the same frequency and exactly the same timing, but with a 90-degree shift. And we will use this to feed a second mixer with the same RF input frequency that will give us the sine output of our mixing stage. If we sample both, then we will get a digital version of this real and imaginary part. We call these the Q and the I samples, and this is in fact our complex sample. Now note the sampling frequency here will determine the bandwidth of our signal. No? So the higher we take the sampling frequency here, the higher the range of frequencies we will be able to process digitally. We will come back on that a little bit later. I will discuss that again a little bit later. Now this is a very nice circuit, and it's actually also being used in this way. We can build an SDR receiver using this principle. Now there's actually an even more elegant way. That is the second method, where we will try to replace this analog part, because as you see, we still have what we have discussed in the first part, this analog stage where we have this mixer and analog oscillator. We have to have some compensation if there are nonlinearities. We have to take care of propagation delay, all these kind of things. Our 90 degrees shift needs to be accurate, all these kind of things. If we have a 1 degree error there, it means that our resulting samples will be incorrect in phase and not actually the correct samples to work with. So all processing done digitally later will have this error margin. So how can we do this? Well, I will first discuss the analog version, and then we go to the digital. We can use, instead of the two mixers with the 90-degree phase shift, we can use what is called a tail-loop mixer. And what is a tail-loop mixer? A tail-loop mixer is actually using a digital circuit to do an analog mixing effect. So if anybody knows the 4066 CMOS chip, it's a typical analog switch. These are analog switches with a digital input. So you have an input and an output, and if you put a binary 1 or 0 on the switch, it will open or close. No? There are typically 4 of these switches inside of these chips. So what you see here could actually be a 4066 CMOS chip that we feed with our RF signal. Now what we will do is we will close these switches successively. We will create a switch with 4 outputs. No? And we will move this switch, we will rotate this switch with 4 times the frequency that we normally would use as a sample frequency. So instead of the normal sample frequency, we will use 4 times that sample frequency, what will produce us on the first output of this switch. We will get a normal sampling at the sampling frequency. Okay, because every four clock pulses of the frequency that we use to control our switch now, we will get an output signal on this first output. You see the capacitor there. What we actually have built here is a sample and hold circuit. So the switch is closing, the first switch. The capacitor is being charged. It's taking the value of the the sample, and it maintains that level theoretically until the next time the switch is open or closed. Of course, on the next clock pulse, the first switch will open and the second one will close. And as we are at 4 times the normal sample frequency, we actually have a 90-degree shift here. If we have an incoming sine wave, it means that the first sample we take on the first output will be at 0 degrees, the second sample will be at 90 degrees, the third sample will be at 180 degrees, and the fourth sample will be at 270 degrees. So we have 4 outputs here, and they are all 90 degrees apart, which is interesting because we can take the first output and the second output, and there we have our 90-degree shift, which is actually our I and Q signals that we need to compose our complex sample. Now, it's a pity that we would lose this 180 and 270 degree signal and not use it, because we are sampling at 4 times the rate, and we're just throwing away two samples of that. So analogically, this is being solved by using operational amplifiers. What we will do is we will take the 180-degree signal and the 270-degree signal, and we'll feed it on the negative input of an operational amplifier. So what we will do is we will add another 180 degrees. So 180 degrees plus another 180 gives us a 0-degree signal again. And the fourth output, the 270 degrees, we add another 170 degrees, which gives us actually a 90 degrees signal again, but one sinusoidal wave later. But it's also the 90-degree signal. So we can actually save our lost samples and use them again as a complex sample signal. So this is an analog Taylor mixer circuit to produce analog IQ signals that after that needs to be sampled still. So the IQ outputs of these op-amps would then go to AD converters normally. Instead of this, what we will do is we will use an AD converter and a sample and hold, and we will run the AD converter at 4 times the sampling rate that we would normally do. So what we have then is we have 4 times as much samples coming into our digital stage, and then we will make a digital switch that is actually splitting our incoming samples, into 2 different streams. It will send the first sample to a first stream of outputs, and the second sample to a second stream of outputs. The third sample, it will output on the first stream, but inverted. Remember the 180-degree shifts in the analog circuit? So we will mathematically invert it here inside the digital stage. What we will next do with the first stream is delay it 1 sample. Why? Well, in this case, we have the sample is 1 and the sample is 2 arriving at the output of our digital circuit here at the same time. So we will have a digital I and a digital Q signal making up a complex sample in digital form using only 1 AD converter. Of course, this AD converter needs to be more expensive, higher in bandwidth, because it's sampling at 4 times the sampling rate. But the advantage is we got rid of the complete analog stage. So let's combine this with what we have seen in the first part of the talk concerning the using the aliasing as our to our advantage. We can use oversampling at the input of our newly formed digital Taylor mixer. So we can use oversampling and use only 1 AD converter, but with a higher frequency, with a higher bandwidth, sampling at 4 times the sampling rate that we would normally use, and we get a completely digital signal to sample a high frequency RF signal and to produce complex IQ signals. So this is what we call a direct IQ sampling technology. So it depends. This is not always used. Sometimes the analog version is used, sometimes this one is used. It all depends, of course, because you can imagine that this oversampling technique has limits to it. You can't really use in a very efficient way the Nyquist, the 150th Nyquist zone. That would give some problems. But there is a practical range of Nyquist zones that are usable to use this oversampling method. And this Taylor mixer, in this sense, of course, is interesting when our required bandwidth at the output is not too high. The whole IQ sampling system has some consequences. No? And what are these consequences? Well, the side effect of IQ sampling is that it is producing positive and negative frequencies. And this is something that is often misunderstood, because it's something strange, negative frequencies. How on earth can you produce negative frequencies? And the second thing is that the sampling rate versus the obtained bandwidth, the formula that we will have to use there is changing. So the sampling formula normally, the Nyquist-Shannon formula, that we need to sample at double the frequency of the highest frequency that we need, this will change. We will discuss this also in the continuous slides. For this, to understand both these consequences, we start with a normal signal mixing again. So in a normal signal mixing situation, we have some kind of a bandwidth in a higher frequency that is our interest bandwidth. And this, due to mixing it with a local oscillator, is going to be transposed close to 0 or close to an IF frequency. Ultimately, our objective will be to have it close to 0. This will be our baseband. Now, after that, we do, for example, sampling, and then our sampling frequency needs to be higher than needs to be the same or higher than the double of the bandwidth that we want to use. The bandwidth is the whole stage from 0 up into half the sample frequency. This is going to be our first Nyquist zone. That will be our zone of interest. Now, what happens is if we have a random carrier in this bandwidth, that is of our interest, it will be transposed into our baseband at this location. Now, the problem with a normal signal mixer is that we can have mirror signals. And what is this mirror signal? Well, this signal mixed with a local oscillator will also arrive exactly at the same frequency into our baseband. And the reason for this is that in a normal signal mixing situation, it is impossible to distinguish whether the mixing signal is F1 minus F2 or F2 minus F1. So the local oscillator could be our F1 or it could be our F2. So if we have these carriers, the red and the green one, mixing with the local oscillator, both of the products will arrive in the baseband at the same place. This is why in an analog circuit, we will always use an input filter in our circuit. Our RF input filter will always filter out these mirror signals, and in general, we will try to have a local oscillator that is sufficiently high above or sufficiently low below the bandwidth that that is our interest bandwidth, in order to make this analog filter less complex, because the closer we take the local oscillator to our bandwidth, the sharper this filter will have to be to filter out the mirrors that could appear next to our local oscillator on the other side. Now, if we take complex signal mixing, we have a different situation, because a sine wave in the time domain, whether it is F2 minus F1 or F1 minus F2, it will appear the same thing. For example, if our local oscillator is 100 megahertz and our signal of interest is 110 megahertz, well, we have F2 minus F1, 110 megahertz minus 100, that will result in 10 megahertz. In the other situation, we can have the mirror frequency on 90 megahertz. Then we will have 100 megahertz minus a 90. That will result in 10 megahertz as well. But what is actually happening is it is 90 megahertz minus 100 is resulting in a minus 10 megahertz. Of course, minus 10 megahertz doesn't really make sense. In the time domain, it's just the same thing. It's a single sinusoidal wave that is progressing into the time and changing in amplitude. However, in the vector field, we can see that if we would have 100 megahertz minus 110 minus 100 megahertz, we would have a vector rotating in counterclockwise direction. And if we would take the 90 minus 100 megahertz, we would have a vector that is rotating in clockwise direction. Now, normally, we can't distinguish these because we only, in a normal situation, analog sampling situation, with a real component only, the only part that we are sampling is the sine axis. So we can't distinguish them. However, if we have complex signals, we also have the cosine axis information, and we will be able to distinguish whether the resulting signal was an f-2 or a 2 minus f1. So if the vector was rotating on in the clockwise or in the counterclockwise direction. So this is actually what we call a negative frequency. It is a vector that is rotating with the same frequency, but in the other direction. To understand this very in a simple way, think of where these vectors originate from. We have an electron motor, and if an electron motor is fed with a sinusoidal wave, it will rotate now. And if we change the phase of the signals that we feed into this electromagnetic motor, the motor will start spinning the other way around. So these are the positive and the negative frequencies. Either our motor rotates in clockwise direction or it's rotating in our counterclockwise direction. Now the consequences is that our mirror frequency now appears in our sampled digital domain as a negative frequency. Our mirror frequency now is below 0 hertz. We have minus 10 megahertz, for example, and this minus 10 megahertz, well, we are digital, it's just a number. So we get, for example, 10 megahertz, it's a series of samples, and they are expressed complexly as a complex number, they just have a minus sign. So mathematically, negative frequencies is perfectly possible. This means that if we would sample a bandwidth around our local oscillator, that we now have our bandwidth of interest that is normally above our local oscillator, but we also have the bandwidth below our local oscillator that we can use, because they will be projected around the 0 hertz line in the frequency spectrum. They will be projected as negative frequencies. So now we don't really need this sharp filter to filter out the mirror frequencies. As a matter of fact, all we need to do now is to filter the bandwidth around this f1. That is that is depending on the sample frequency that we are going to use in our baseband sampling. This will become a little bit more clear in the next slides also. So if we look at it, here we have if we take the example of the Taylor mixer digitalized, we would take oversampling, and then we have this n time fs. So this is our oversampling frequency, and we have the Nyquist zones. So we would be able to sample, for example, from n times fs over 2 up to 3 over 2 times fs times n, so the next Nyquist zone. This will be our sampling bandwidth. So now we are not talking about our maximum sampling frequency, we are talking about our bandwidth. Our sampling bandwidth will not be 2 times f maximum, but our resulting bandwidth will be equal to the sampling frequency. Okay? Of course, disregarding the multiply n factor here. So this is the bandwidth that we are left over after sampling with negative and positive frequencies. So actually, the fs/2 area, the second Nyquist zone, that would normally be these mirror frequencies that would be flipped in frequency, we don't have these anymore. These we will find to the left side of the 0 Hertz frequency axis. Now, what happens if we have a frequency that is outside of the Nyquist zones of our bandwidth? Well, we enter a new Nyquist zone, and now instead of having these low to high, high to low, low to high, high to low flipping frequency pages in our folding spectrum, we have something different. As we have a frequency of interest that is moving out of the range, let me try if I can get my cursor there into the monitor. No. Yes. So if I have a frequency of interest here that is moving, can you see the arrow? Is the arrow visible? Yeah. So as my frequency here is projected here, and as I'm moving up in frequency, I'm going above the Nyquist zone. I enter a new Nyquist zone, and this frequency appears to be again the same as the frequency that I would have here. See, so this is simply the next Nyquist zone. This is simply the next Nyquist zone. And that is logic, because it would be n plus 1 times fs. It would be if I would move my anti-aliasing filter in oversampling, I would shift it just one step up. I would just shift it to the next. You see? So every new zone of 2 Nyquist zones, one above and one below the sampling frequency, is actually what is projected time and time again around the 0 Hertz axis. So this is often misunderstood. You see here in the complex number field, we work, once we are in our digital domain with our complex samples, we actually work with positive and negative frequencies. So we discussed hardware already, how to get IQ signal input samples from an RF signal. And now the second question would be, how do we get from these digital complex samples again to an analog signal? And that would be the same but opposite. It's not completely opposite. What we do here is, again, we start with the IQ samples that we convert back to analog signals with a digital analog converter, and then we will mix them again with a sine wave and a cosine wave. So we have the 90 degrees apart here. However, here it's a little bit different. Although the circuit appears to be quite similar, there is a little difference here, where in the sampling circuit we had the same RF signal feeding into the 2 mixers. What we have now here is an analog addition circuit to add the 2 results of the mixers up. So we get the addition of the 2 mixer outputs. And now I won't do the mathematical functions here. You can do it for yourself. The formulas are in the previous slides. But what we have here is we have these 4 sine and cosine terms here, which produces a quite big formula of the resulting factors of the mixers. And if we do an addition of that, the reduction of this formula, because we will be able to scrap out some of the terms in the formula, will reduce the whole formula up to the simple analog signal again at the output. So this is the output stage variant of what we have done on the input stage. Now here again, the same exists in a Telu version. So we will be able to compose also these complex output samples again for in part in the digital domain before we go back to the analog domain. And these both stages, this will make up our software-defined radio hardware. These are some examples of software-defined radio hardware boards. So we see here typically it's an USB board. We have, depending on if it's an RX or TX combination or RX only, we have, for example, an RX and a TX input for the receive and the transmit. This is going into our board being digitized, turned back into complex samples, and this is the data stream that is being outputted via USB towards a general computing device like a laptop or another computer. So these are the typical USB boards that we would use here as software-defined radio in general. Of course, there are some consequences if we would like to use this in a satellite setting, especially when we go to CubeSats. This will offer a few problems. Now, if you look at the software part of it, up until now we have discussed how to get the RF signals into the general computing device. We will use software to process these signals afterwards, and we would like to do so in an easy way, of course. Luckily, there's a software platform that has been developed over a lot of years now, I think close to 2 decades, and that is GNU Radio. So GNU is from the GNU is not Unix, Linux type of software, so it's open source, and it's a software package completely built for a software-defined radio development. So it's a framework. It's modular, so there can be modules added to expand its possibilities, and this, as I said, it's open source. On top of GNU Radio, we have something called GRC, what is short for GNU Radio Companion, what is actually a graphical interface. It's a front end for GNU Radio that allows us to design in a graphical way software code that lies underneath the processing with the samples. And we talk, in this context of GRC, we talk about flow graphs. So instead of analog circuits, where we have analog stages like filters and stuff, we talk about flow graphs, and these flow graphs contain blocks. So this would be a typical example of a flow graph, and this flow graph with a lot of blocks successively connected to each other produce some kind of an effect. And in this case, this flow graphs is exactly the same as an FM receiver. So we have on the one side the digital samples, complex samples coming in, a certain bandwidth. Due to the processing on all the successive blocks, we will end up with a sample series going to the sound card of this general computing device that will produce an audio signal there exactly as a receiver would do, except that the whole processing now is done in a digital fashion. Now, to take a closer look at the flow graph, and maybe after this stage I can put a few minutes pause. I don't know, because 3 hours in one go is maybe a quite long trajectory for one go. If we look at the flow graph here of this FM receiver, and we take this first stage, the blue area, what we see here is we have the line suite source. This is actually the digital representation of the hardware board, as you have seen on the picture before, with the signal, the complex signals coming in. And of course, via USB, we will not only take these samples into our general computing device, but we will also be able to control certain parameters of the hardware. For example, here we have the RF frequency set to 105.7 megahertz. This means that if we take the first model, our local oscillator in the first stage, having the 90-degree shift model of our IQ sampling principle, we have the local oscillator set here to 105.7 megahertz. This will produce then, after the two mixers and the sampling stage, a series of samples, and this series of samples we can choose the sampling rate, and here it's set at 1 megasamples per second. This GRC actually allows for adding blocks like variables, and I have here a variable called samp_rate. These are variables that you can use in all of the blocks so that you don't need to adapt all these parameters in all the different blocks if you would want to make some changes to your flow graph. So now I have a variable called samp_rate with a value of 1 megasamples, and I can use this as a parameter into the different blocks. 1 megasample of sample rate means that I have 105.7 megahertz as local oscillator, and I have a bandwidth of 1 megahertz around this local oscillator of bandwidth captured by my software-defined radio. So I have 1 megahertz of bandwidth, and we have to be cautious here because it is actually 500 kilohertz above my local oscillator and 500 kilohertz below my local oscillator, the positive and the negative frequencies. So I have this 1 megasample sample rate stream of samples going out of my hardware here into my flow graph. And the first thing I will do is put these samples to a processing block, and this is a fast Fourier transform processing block. So we will do mathematically a fast Fourier transform that will give our sample series, which is a time domain series, visualization into the frequency domain. If we do so, this is the result. So we see above I have the tuner frequency. I will go back. We have the WX GUI slider. These are elements that you can add to the flow graph to change parameters when you are in runtime. So I have a slider here for the frequency with a minimum of 88 megahertz and a maximum of 108 megahertz. And this slider appears when I'm running my flow graph on top of my output display here, and I can take my mouse and move the slider, and this will actually change the tuning frequency. The result here is the spectrum, and it's tuned exactly here to a radio station that is a 97.5. And what we see here, a radio station, FM radio station in the radio band is typically 200 kilohertz of bandwidth. And this 200 kilohertz of bandwidth is here presented as plus 100 kilohertz above the zero line and 100 kilohertz below the zero line. So our 0 hertz frequency line is actually the middle of our frequency of interest. You see, so we have a down conversion actually to 0. We have a down conversion. Our baseband is below and above 0 hertz. So now I have a 200 kilohertz signal, but as we can see there at the 400 kilohertz mark, there's another radio station appearing in the spectrum. So we're not interested in this signal. We only want to have the one that is on the center frequency here. So what we will need is we will need to filter out only this radio station that is of interest to us. And we can do this, and this is strange because normally in analog situation we would need a bandpass filter to filter out this 200 kilohertz. Now we need a low-pass filter because, well, what is a low-pass filter? It's from 0 hertz up to a certain frequency. And now we have a low-pass filter that will filter frequencies out from 0 hertz up to 100 kilohertz. Now I'm trying to get my pointer here. So we have a cutoff frequency set here to 100 kilohertz. But we have complex samples, so it's actually a low-pass filter in both directions of the frequency spectrum. It's a 100 kilohertz cutoff frequency on the positive side of the frequencies and of the negative side of the frequencies, which gives us a total of 200 kilohertz of output sample bandwidth. Okay. The sample rate, however, is still 1 megahertz, 1 megasamples a second. Now, the point is that I have a series of samples of 1 megasamples per second, but I have only inside this sample range 200 kilohertz of bandwidth that is interesting to me. This is not so interesting in the context of a CPU, because it means that our processing unit will have to process 1 megasamples a second, and only 200 kilohertz of bandwidth is actually useful for us. So what we will try to do is reduce the number of samples here, because they are not interesting for us. And that's very easy. We have seen it in the previous example, in the beginning of the slide series already. We can simply keep 1 out of n samples. This is what we call decimation. So the next block we have here is a decimation of 5. Every 5 samples will keep only 1. And in this way, we will reduce the sample rate from 1 megasamples per second down to 200 kilosamples per second. And this 200 kilosamples per second will contain my 200 kilohertz bandwidth with all the signal information that I need. The next that I can find in my circuit here is a simple squelch block. So this is also what we have typically in an FM receiver. If there is no tuned radio station, then normally we would receive only noise through our speaker. That's very annoying. So what we will do is, if we don't perceive any carrier signal in the frequency band of interest, then we will try to cut off our audio. So instead of cutting off the audio, what we'll do here now, we will have a digital calculation of the signal-to-noise ratio. And if this digital signal-to-noise ratio calculated drops below a certain level, what I will do is not stop the sample stream, because that would give problem in my flow graph. I will replace the value of the income samples with 0 samples. So the value of the samples going out will be 0 plus J0, which will produce nothing. But I will have a valid sample stream, so the rest of my flow graph will still be capable of processing it just as it would do normally, only it will contain no information. Okay, and I have a GUI slider here where I can set the squelch level again, and I have a checkbox that I can add to my flow graph to switch my squelch on and off. So you see, it's a real graphical way. I can just put blocks in my flow graph and create my receiver with buttons and switches just the way I like. Now the next stage is, I have this 200 kilohertz bandwidth. Of course, this is a modulated FM signal. I will have to demodulate it. Now I will go from a modulated signal to a demodulated sample stream. The thing is, I can't really feed complex samples to an audio card. And a complex audio signal doesn't really make sense. We can only listen to a normal sample range coming out of an AD converter from a sound card. So what I will have to do as a second step is to go from complex signals to a more simple sample range, and that is, for example, floats. Now inside GRC, GNU Radio underlying, we have a whole set of variable types that we can work with. So the one we've been working with so far will be a complex float of 32 bits, which is a complex number, which is a float of 32 bits plus J, another float of 32 bits. That's the complex float sample. And we have a whole set of other variable types available, and we will go to, in my demodulator stage here, to a regular float of 32 bits. So no longer a complex signal, a normal sample series, but of 32 bits float value. Now the WB-FM is a wideband FM demodulator. It's a quadrature demodulator. How it works inside, would lead us too far. It's just software, mathematical representation. Again, just like we discussed with some other parts before, mathematically, you can also demodulate from this baseband 200 kilohertz, the analog output signal in a digital sample representation form, of course. So the next thing that we would do then is, if you would look at the output, we still have 200 kilohertz of bandwidth coming out of demodulator. But now we have the demodulated bandwidth. And this demodulated bandwidth looks like this. Because inside the demodulated signal, we have a lot of things inside of there in an FM signal. It's typical in a stereo FM signal, we have more than just the audio. We have the mono audio, which we typically find between 0 and 17 kilohertz. That's the normal audio. We can feed that directly to a speaker via amplifier, of course. Then we have a pilot tone, and this pilot tone is used to recognize in the receiver, in an analog receiver, normally if the transmitting station is using stereo audio or mono audio. If this pilot tone is there, then it means the signal that is being transmitted is in a stereo format, and in this case we will have a new piece of bandwidth that is filled with the differential signal of the left and the right channel of the audio that can be used in the demodulator to recompose the left and the right signal. This is typically done in single sideband modulation. And even higher in frequency, we find some digital signals that contains the RDS information, for example. Okay, so this is not really interesting for us in the satellite context, but it's just an example of demodulating a signal. What we will need here, because we are building here just a simple mono receiver, we will need to filter out this pilot tone, all the DSB or SSB information, the digital RDS information, and so on. So the next part we will have is a low-pass filter. So this low-pass filter, as we can see here, has a cutoff frequency of 17 kilohertz. The sampling rate is still 200 kilohertz. So the cutoff frequency is 17 kilohertz. So we keep only the mono audio part. And these now are a discrete 32-bit float sample series. The next thing we have is that we have 200 kilo samples per second, but we need to get to our audio card, and our audio card is actually working with a sample rate of 48 kilo samples per second. So we need some kind of a conversion from 200 kilo samples to 48, but we can't use the simple decimation method because we can't drop half a samples or a third of a samples. So that's impossible. If we do single drop sample dropping, we can drop 1 out of 2 samples or 1 out of 3 or 2 out of 3, but we can't drop a half a sample, for example. So what we will use is we use an interpolation stage, and this is what we call a rational resampler block. We will in fact make more samples first before we do the decimation. And making more samples is quite easy. We simply add empty samples. So we will go from 200 kilo samples per second. We will multiply the sample series by 6, and we will go up to 1,200 kilo samples per second. Why? Well, there we have a real number, again, quantified. We have a real number that we can use, 25, that we can use to divide and end up at 48 kilo samples per second. So this is what's happening into my rational resampler. Then I have a multiply constant. So I have these discrete samples values, which are floats, and I can mathematically multiply them with a value. Now I'm multiplying them with 0.1, and this is actually a volume control, because the height or the value of the sample is actually the audio amplitude level. So if I multiply the output sample stream here with a value, I get a volume control. And these samples I can feed to my audio card of my my computer, for example, or laptop, or other general computing device, and what I get is the audio of the FM broadcast radio station, completely done digitally. And I think this is maybe a good point to make a small break. Let's say 10 minutes, or is that fine?
Yes, that's okay. 10 minutes to get a coffee and
Yeah.
to clear your voice and have a water, because indeed speaking for 3 hours is quite exhausting. So we'll see each other back at 11:30.
Okay.
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 I don't know if everybody's back. And if you can still hear me.
Yes, I can hear you.
Shall we continue, or maybe, I don't know if there's a hands up function on this Zoom also.
I guess you can resume.
Okay. There's one last thing I need to tell about this flow graph, and it's already logical. Of course, we put the multiply constant here before, sorry, after the rational resampler. Why? Again, for the same reasons. If you have to multiply all the samples with a value, it's of course a lot less stressful for the CPU to do this with 48 kilosamples per second than to do this with 200 kilosamples per second. And it's not interesting. The information isn't really valuable anyway. So this is, of course, the second reason why we will reduce the sample rate downwards as well. So two reasons in this case: one, to adapt to the physical sample rate of the hardware; the second one, again, to reduce the processing of the samples, the processing required for processing the samples. Now, considering what we've been talking about so far on this on this flow graph, what one can realize is that every block on our flow graph here is putting stress on our CPU. All these samples need to be processed in all of these blocks. And not only do they need to be processed, they need to be processed rapidly, because the next block every time needs the previous samples processed before it can work. So we have a huge amount of stress on the CPU to make sure that all the samples arrive at the next block in time, and that it produces a sufficient sample output for the next block every time. So the thing is that a CPU is actually a sequential device. No? It will process instructions one after the other. And we could reduce this stress, for example, by allocating a certain processing of a block in our flow graph to a core of a CPU when we use a multi-core CPU. But of course, that is limited. We have 4, 8, 16 cores maybe. So also this is limited, and we have these timing issues. We need to make sure that the samples are every time in time into the next stage. So software-defined processing of samples requires actually a lot of parallel processing, whereas CPU is typical sequential. Now, as we have this in between the blocks, it is the same problem we have inside these processing blocks. I will take a digital filter as an example. Now, what is a digital filter? If we just quickly, if we take an ideal pulse in the time domain, it's called a Dirac pulse. This gives us, if we look at it in the frequency domain, it will give us an infinite number of frequency components, all components above this on the spectrum from 0 to infinity. Now, if we put this into a black box filter, we get this Dirac pulse at the input, we will get some kind of a pulse at the output. Now, if this pulse is finite, we will call this filter a finite response filter. So these finite response filters, this digital version, is actually what we've been using so far when we were using the low-pass filters, for example. The low-pass filter was digitally a finite response filter. Now, if we look at it in the frequency range, so we have the direct pulse is the same as the whole set of frequencies, gives us some kind of a frequency response at the output. And how do we build that? Well, we'll build it by actually delaying and adding samples together. For example, if we add sample number n together with sample n-1, we get an average. And what is average? Actually more than a low-pass filter. If you take an average of signals, then all the high-frequency components will be removed. So this is a stage of such a filter. And as we add more of these filters after each other, we can actually create a certain frequency response. We can create a sharper low-pass filter, or we can make even a band-pass filter or a high-pass filter. So this is a typical finite impulse response implementation. So these kind of filters, they consist of taps. So you have one sample that is multiplied with a certain factor, it's delayed, and it's added together with the other samples that are coming in. Of course, these samples, they can only be processed when the previous one is already processed. No? So as the number of taps in a filter increases, it increases also the CPU load. Because if you have 4 taps, well, the last tap can only calculate if the previous have their result shifted into it. So we need a kind of parallel processing here to make this FER filter also. But we already had these parallel processing between the blocks. So we have actually a requirement for a huge amount of parallel processing. Which leads us to the fact that CPUs are maybe not the perfect device in software-defined radio, especially not when we are going towards a satellite environment. Now, this is a good stage to make a little segue into something that is often misunderstood. A lot of people who start to work with software-defined radio and flow graphs, they misinterpret the sample rate. Many people make a mistake of confusing the sample rate with the processing speed of the flow graph. So you think, well, we have 1 megasamples coming in, then there's processing, and there's 1 megasamples going out. This is not really the case. As a matter of fact, a flow graph is being processed as fast as possible. And to understand this, the easiest way is to make a small comparison with what we do with file copying. Now, imagine you have a movie of one hour, an MPEG-4 movie of 1 hour. How long does it take to copy this movie? 1 hour? No, you can copy this movie a lot faster. Now, this movie contains inside images at, for example, 24 frames per second. So this 24 frames per second is actually some kind of a sample rate, right? So despite having the sample rate being 24 frames per second, we can still process this movie a lot faster than these 24 frames per second. As a matter of fact, the frames per second of this movie is some kind of a metadata attached to the file of the values of the data values of this MP4 movie. You see, so the sample rate is a parameter that belongs to the data, the sample data. It does not necessarily limit the processing speed with which these samples can be processed. And this is often misunderstood, especially with starters in working with flow graphs. And a good example is this. What is determining ultimately the speed in the flow graph? It is the hardware. If we have an SDR USB device that is feeding samples into my flow graph, it is the 1 megasamples per second of samples coming out of the USB that is determining the speed with which my CPU will have to process the samples, because that's the speed with what the samples are coming into my computer. If it would process the samples faster, well, it would run out of samples to process. If it would do the processing too slow, well, we will get overflow. The same counts on the other side. Imagine that we would have what we can do in GNU Radio. We could have a virtual source. We could have a signal generator, a sinusoidal signal generator that is completely producing a digital sample stream in the flow graph, so without coming from hardware, just mathematically calculated samples. And these samples go to a sound card, for example. Well, the processing speed of the samples will be the maximum speed this hardware device accepts the samples. In the case of sound card, for example, 48 kilo samples per second. If we would process the samples with a higher speed coming from this virtual source, while we would get a buffer overflow in the sound card, if we produce the samples too low, then we get an underflow and the sound card would get choppy sound. Okay. Now, if we would take a completely virtual flow graph, what is possible? We take a sample signal source and we feed it directly to, for example, an FFT block to see the spectrum result of it. Now, if my signal generator has a sample rate set of 1 megasamples per second, at what speed will these samples be processed inside my flow graph? Well, at the maximum speed my CPU allows. So if you would run a flow graph like that and you check your CPU load, it will go up to 100% and even more, depending. Some cores will even be overloaded, but you will go up to the 100% load of the CPU, even though it's not necessary. So it means that although the sample rate is 1 megasamples per second, it's well possible that up to 10 megasamples per second are being processed because it's metadata. Yeah. So for this reason, in a flow graph, if we use only virtual sources and sinks, we will have to add a throttle block. And this throttle block is doing nothing more than to squeeze down the speed with which the samples are being processed by the CPU. It creates some kind of a virtual hardware that is slowing down the samples to a certain rate. So the sample rate set here will be the sample rate that the CPU will process the samples. And this can be higher than the sample rate of the generator. For example, we have the signal source processing, putting out samples with the metadata set to it 1 megasamples per second. The throttle can be set to 2 megasamples per second. And the FFT can be set to 1 megasamples per second again. So the whole flow graph will be processed with a rate of 2 megasamples per second, although the sample rate actually in the system itself is 1 megasample per second, just like we would copy a movie from 1 hour with double the speed. Okay, so this is similar. And a lot of people make a mistake here in creating flow graphs. What they will have is they think, well, we did everything right, but our flow graph is running with an overflow of samples, or we get an underflow of samples in the flow graph itself. And this is just because they didn't really capture exactly the difference between the sample rate set in the blocks and the processing speed of the samples by the CPU. Now the question was, after the segue, how do we solve this need for parallel processing? Of course, the perfect solution for this is to implement software-defined radio in FPGAs. Now, the field programmer gate arrays is actually the software and hardware solution. It has the advantages of both. It's flexible, it can be updated, but it has hardware-like characteristics. So it allows for high-level parallel processing. So, for example, this FIR filter can be implemented exactly the way that we've drawn it. We can make an addition circuit. We can make a delay circuit these are simple flip-flops. And these flip-flops are very easy to implement in this FER filter fashion inside an FPGA. So this is perfect. We can make this FER filter block with 50 taps, and it won't consume a lot of our power and CPU. Because here we have the parallel processing done, the power requirements dropped, and the processing requirements drop. So very good. Now, let me switch to a note here. So the thing is that today, FPGAs are in no way optimized for software-defined radio use. So if there is any candidate PhD who wants to work on chip design and who wants to make like progress on FPGAs for SDR applications, there's a huge opportunity here. So first of all, FPGA, they do exist. Of course, you need mil specs or space specs. They need to be capable of handling a lot, a bigger temperature range from minus this number or up to a high temperature range. That this is one parameter. Of course, there are of course already FPGAs due to mil specs, but also what is a possibility here is to integrate sections into the FPGA that are optimized, for example, for this AD converter stage, like a Telu mixer stage in the digital form, or for example, predefined FER filter stages. So it's possible to create FPGAs that have certain physical blocks inside of them that are predefined and connected then to inside the FPGA that can actually create a far more interesting chip to use in an SDR setting than is currently on the market. So that's an opportunity here for somebody who would be interested in it. Now, what is the disadvantage here? The disadvantage when we go to FPGAs is that we don't have these easy design tools like we have in a CPU setting like GRC and GNU Radio underneath. So we don't have the already ready blocks like the SDR block library, where we have a ready-made, ready-written FM decoder, where we have QPSK modulators and so on. So libraries that we can just use to build our flow graph with. We don't have this in FPGA. And it's not something that we can easily transpose. You can't just simply take the code here and convert it to VHDL or Verilog, because VHDL or Verilog is not a programming language in the sense of sequential programming languages like the way we are used to it in the CPU setting. So VHDL code is completely different. It's another mindset, and you can't just simply transpose code to it. So one of the solutions here would be that we make the drawings in GRC. Let me first explain something more about how GRC works, how the software model works behind it, then we can go to the solutions. So the software model in GRC works like this. The GNU Radio companion, if you draw, you put the blocks and you connect the blocks, is creating an XML file. And this XML file contains all the parameters of the blocks that you have been using and the connections and the settings like the sample rate and so on. Now next, when you compile such a flow graph to code, what's happening is it creates Python code. And actually the parameters and the formulas, the variables that you use inside these flow graphs are in fact Python variables. So you could even use Python expressions there. And the code that you get after compiling the XML code is Python code that is gluing the existing block functions together. Now these block functions itself are mainly written in C, C++. Why? Well, Python, of course, is an interpreter language. It's much too slow to do the processing of samples, for example, of a fast Fourier transform. So we have three levels. You have the XML. We have the Python code that is created that is gluing all the C, C++ blocks together. And this is, in fact, our software model inside the GNU Radio companion. And finally, the code that we made with this, we can move this code once it's compiled and ready. We can use it to an SBC board, single board computer, running on an ARM processor. For example, instead of a CPU Intel on a laptop, we can use it there without the necessity of installing the GNU Radio Companion. All we need is the C, C++ libraries and the Python code that is already compiled here. Because we also used compiled Python. And compiled Python is faster than regular Python, the interpreter version. So in GNU Radio, there is the compiler version of Python code being used. Now this is the graphical overview. We have GRC produces XML, the Python that is used to connect the C, C++ blocks, and it could be also a Python block. Now, if the processing speed is low enough, it can be written in compiled Python, for example, as well. And this is actually a possibility that we have in GNU Radio Companion. We can use a block there that is called an embedded Python block. And it appears as a graphical block inside GNU Radio Companion, but we can write the Python code ourselves. And if we look at snippets code from how this looks like, we see there we have some parts in this. It's of course object-oriented. You see there self.block null source. That's the source on the left-hand side of my block, and the samples are going through my block to a null sink. These are sources and sinks that do nothing, just as an example here. And you can see here that we are pushing complex samples from one to the other. It's a way of describing these blocks and connecting them together. You see the connections there. So we connect my own block with the sink, and then we connect the source with my own block. So this is the Python code example of what we see in the flow graph here. Inside the Python block, we can define functions to process the samples any way we like. We have here a list, a complex list of NumPy, so the Python NumPy library, complex NumPy lists. And this list we can process, do, for example, multiplication. Then we create the same thing as the constant multiply block. And we have an output list that is actually putting the output samples back into the flow graph stream. And the processing itself is done in a function called work, or a method, as we are using object-oriented parameters, object-oriented terminology, of course. So the work method here is actually where the work is being done with the samples. So if you would like to write your own block inside GNU Radio Companion, you can do so by adding this embedded Python block and defining the code here in your work method. Now that we see how these blocks work, how the flow is in the framework, we can look how a possible solution would look like if we would do SDR FPGA design. So where we have the Python C, C++, we need, for example, a VHDL conversion tool. That would be an option. So we take the same model and we would try to write some kind of a compiler that is compiling these Python blocks into VHDL code. But that's the difficult part. You know, remember, the VHDL is not something that can easily be used to transpose code from a sequential system into VHDL code. That's not a very good solution. The conversion would be very hard, and also, even if we would be capable of doing that, it would absolutely not result in an optimal use of the FPGA cells. With no doubt, the resulting VHDL code would be bad. It would work, but it would be bad, as it would by no means optimize the use of the cells in the chip. So this is not a good solution. What is a good solution is that we would keep this model, we make the drawings in GRC that is producing XML code, no change there, but that we would have a possibility to compile this XML code into VHDL glue instead of Python glue, and have a library of the VHDL blocks with all the software-defined radio functions, so that you would have a VHDL block FER filter, VHDL block QPSK modulator, and so on, that you will have the whole identical library as a GNU Radio Companion to your availability inside this kind of system, that you could make the drawing, compile, and get these VHDL blocks glued together via VHDL glue. And then what we have, this resulting code, we can load directly into the FPGA, and we would have an SDR system running directly on the FPGA coming from our flow graph. So this would be a very good solution. So here again, if anybody is pursuing a PhD in software design or want to focus himself on or herself on this is a very interesting space to work in. So what is an opportunity here is to create these kind of SDR function libraries, to create a model similar to what we have in GNU Radio, but for VHDL or Verilog, depending on what you prefer. And this would be a huge advantage for SDR in space applications in the space industry, because of course you can realize that using CPUs in a tiny box of 10 by 10 by 10 that has a lot of heat, that needs a lot of parallel processing, it will consume a lot of power. This is really a suboptimal solution. So the FPGA solution is really the way to go for satellite industry. But unfortunately, this is missing a little bit. So this is a great opportunity for people who would want to work on this. And with this, I arrived at the end of my talk. I hope you found it a little bit interesting. I don't know how much of it that was new or just a repetition. I think I will soon find out. We'll leave some space for the Q&As. We have time enough for that now.
Okay, thank you, Geert, for this interesting presentation. Are there any questions of the participants? You can either put a question in the chat.
Maybe verbally would take my advantage, because I can't, as I'm presenting, I can't see the chat for some reason.
Yeah, okay. Or yeah, you can just ask your questions.
Maybe I have a question in how far everything was new or not to this audience, because of course I did not have any background information on your knowledge on the subject. So that's an interesting question for me to know. How much of it was new and how much was it a repetition?
It seems everybody is a bit shy. Don't be shy.
Although software-defined radio exists quite a long time already, it's still rather new in academic fields outside of this typical application. For example, in the space industry, it is quite recent, as we saw in the first slides. A lot of things are still using all the analog stuff just exactly like 30 years ago.
I know that in ESA they developed their own space-grade FPGA. Do you think in ESA they will be using software-defined radio, or will they still use the old-fashioned type of radio? Do you have any idea? I
don't really know. I think a lot FPGAs will certainly be used to optimize processing inside of satellites, but I don't think necessarily they are used in the RF stage so much yet.
Mm-hmm. Mm-hmm.
So the RF stage, especially when we go to the higher orbit satellites, this is really a very conservative market, because as of course, as you go further away from Earth, you need a high power output. What you see is that they typically still use the traveling wave tube amplifiers. You have the circulators, all the pipe plumber type of RF stuff, and it's quite conservative in that stage. I know. On lower orbit, of course, there's a huge evolution. There's too much evolution for me to follow. I don't know exactly, for example, in the constellations, how fast it's going for the moment. I presume very fast, because if you see that just, I think it's 2 years ago that the first test satellites were launched, and now like half the constellations are up there really. So.
Okay, question is, will this presentation be on the site? Obviously, the presentation, my presentation of the FPGAs and this one will be made available, but we don't know yet to which channel. So we still have to, but we will be informed in due time, and you will be too, so that we can put our presentations there. We also hope that in the Spacecom project that you get the opportunity to come to our campus, so that we can do some practical work on both of these topics. But obviously, the international mobilities are on a standstill at the moment for known reasons. So, but we'll see if maybe some later on the project we will be able to welcome you in Antwerp, or maybe we can we come to Uzbekistan with some of our hardware to make some demos and some practical work on these things.
Maybe also to expand a little bit on my answer on the previous question of Dirk. For the geostationary satellites, I know for a fact that it's still the traditional way. That was the area that I've been working in for a long time, and no, it's quite traditional. Also because there's a lot of financial interest to keep it that way. As you've seen, the ground stations, that's the main business model actually. Also, satellites on geostationary orbits are typically quite big, quite expensive. They're expensive to launch. They have huge assurance policies. So what they try to do, of course, is maintain the status quo as long as possible in order to get an optimal financial result from their investments. So the typical development goes slow there. Also on the ground station side, although faster than, of course, in orbit side. For example, the digital modulations was already something that has put a lot of stress on the side of the satellite operators in the first stage. Of course, now everybody's used to it. But of course, using the digital modulation techniques going up to, for example, the DFBS3 and the high PSK ranges is reducing the bandwidth, and bandwidth selling is actually their core business. So that's why things are going slow. It's actually on purpose a little bit. It's a financial interests that are slowing the business speed on the technological side down.
Yes. I have a technical question here. How to take into account the delays in the circuits when digital signal filtering?
Yes, so that's exactly why we need these high-speed CPUs. You've understood directly one of the problems that we have in software-defined radio. That's the delay in the whole flow graph. Of course, every processing will add some delay to it, but we have this in analog circuit as well. This is often underestimated, but analog circuits also add delay to a circuit. Of course, it's of another range, but it can be a problem there as well. The difficulty with analog propagation delays is that it's very unlinear. So if you have a certain bandwidth, the propagation delay on a certain frequency risks of being different on another frequency, which is causing a huge set of problems in analog field. So in a digital field, the delay will be higher, but it's linear. So you get rid of a lot of problems on that side. One thing to add to that, and that's not really to do with the delays, but one advantage, and for example, these propagation delay problems are an example to it, is that, for example, if you have a software-defined radio and your output stage is producing, for example, a harmonic signal. Yeah. So what you would do in an analog circuit normally is you will have to filter it out. You need some kind of filter to get rid of this harmonic signal, because you don't want this harmonic signal to go into your amplifier and to your antenna. So, but imagine this signal appears later on. For example, traveling wave tubes have a typical problem that on the long term they might have the effect that they start to oscillate on a certain frequency input range. So this is a known problem. So how do you do that? The problem is, once this kind of amplifier starts oscillating, the noise at the input on that frequency is sufficient to trigger that event. If we take the harmonic signal and the output signal, what is maybe an easier example to understand, instead of filtering the output signal, what we can do and this is the huge advantage of software-defined radio, is in the digital processing, we will add the inverse signal digitally of this harmonic to our sample range. No? So we will add a digital inverse signal of the same amplitude but inverse phase digitally to our sample stream that will compensate for the harmonic that would appear normally at the output of the DA converter. So this way you can filter this harmonic on the outside you can filter this analog problem at the output in a digital way before the signal leaves the digital stage. So this is a huge advantage, of course, especially when you have stuff that is already in space. See, so this is one of these advantages that only appear once you start to use it. That is of course almost unmissable when you move to applications in orbit. Now, one thing about the propagation delay, of course, that's why I was saying that there's a huge opportunity for people who are pursuing a PhD in chip design. It is to create FPGAs that are optimized for this. Now, having some of the blocks implemented physically already, because they are always being used, for example, these FER filters, inside the same wafer of the FPGA inside the chip design. So having non-FPGA blocks integrated with the FPGA, what is often done in a practical application of FPGA. Sometimes you have a small CPU integrated into the chip itself. So these kind of combinations are often appearing. You have AD converters that are integrated in the FPGA chip. So these kind of optimizations of FPGA chips can, of course, reduce this problem of propagation delay in a software processing equivalent of an analog circuit. I hope that answers your question sufficiently.
Okay. I thought Xilinx was developing such a kind of FPGA. It's called an RF SoC, so an RF system on chip.
Yeah.
They are expensive.
Yeah. So they are coming into market now. Mm-hmm. And one of the driving factors is, of course, these CubeSat constellations, because there's a huge requirement for them all of a sudden. Before it wasn't interesting because, you know, that there was simply not enough demand for these chips, and to develop these chips it's expensive, and it's only interesting when you can produce them in high volumes. So due to this constellation, it becomes interesting to start to start building these kind of chips. So that is something that is appearing. But what is still missing is, of course, the development platforms that are optimized. It would be perfect to have a new Radium companion system where you can just draw a flow graph and load it in an FPGA and it's done. That would be magnificent. And that would, of course, be an accelerator even more. If this would be available, then FPGAs would be used in satellite all over the place.
Yeah. Maybe the 5G, would that affect the implementation of this kind of FPGAs?
Well, not maybe to put it a little bit broader, cellular systems in general. Cellular systems in general are also looking more and more in this direction because, of course, we have the 2G, 2.5, 3G, 4G. These evolutions are requiring to have a new hardware in the whole network every time and time again. So if the cell structure of the networks would be more flexible software-wise, that we can program them in a hardware sense, this can also speed up the progression of networks from 4G, 5G. Of course, there are limits at the front-end side, but it could also reduce the amount of hardware that needs to be replaced every time. Yeah, I think especially in the low-speed networks, they are looking at that.
Yeah. Okay, so I guess we can talk all day, but if you don't have any.
I've been through my slides a little bit faster than I expected. I think I've been talking quite fast, so I hope it wasn't too fast to follow it.
No, I think I guess it's all right. For some, it will need some more dive into some practical things, but in any case, I think you gave a nice overview of what is possible in a software-defined radio. So I guess we can close up now. I didn't expect to be the moderator today because I just wanted to have a small peek, but here I am. And so I want to thank my colleague here for this nice presentation, and thank you all for listening. And yeah, hope to see you soon somewhere. So good luck with the rest of. I think maybe this is the last presentation of the series.
This one more tomorrow.
Maybe tomorrow. Yes, it's true. Yeah. So thank you for your time, and goodbye.
Have a nice day.